All right, so we're wrapping up our first week, and hopefully you guys have survived. First quizzes were great. Usually the first quizzes aren't very good because people just don't really know what to do. I mean, almost all of them are a 29 or a 30, so that's very good. I do want to remind folks, some of you were trying to email me through Canvas. Don't. I get a notification that somebody tried to email me through Canvas. I don't know who, and I cannot open any attachment you send me through Canvas. It's actually impossible. No, Canvas is for me to put stuff for you to grab. Email me through email. I actually got several notifications that somebody tried to email me and they tried to download a file. I will not open up anything that I have to download. That's an absolute no-no, and you shouldn't either, by the way. If you have to download it to your computer from somebody, in general, I just want to look at the picture. So the same thing, you want to look at the picture and print the picture, because when you download stuff, not only does it take up memory and time and space, that's where all the viruses come from. They always come from downloads, not from opening pictures. So most of you are doing a great job. I didn't open up any of the emails you sent me with your quizzes because y'all turned them in. But I appreciate the fact that you were wise in saying, you know what? By the way, generally, how long did it take you to send me it? In seconds for most people. How long? 30 seconds? Oh, you must have been distracted. Anybody like in the 10-second range? Yeah, it's so simple and so fast, it's like, why not? Again, I don't need you to do that, but it's just wise. Everything that can happen has happened. On your way to school, that's the day that they're doing road work, or there's an accident or a detour, or worse, that is the day you couldn't start your car. I've had some of the greatest excuses ever for people not getting to class. I had one a few years ago. Student was able to get to class, and so he texted me a picture. There was a house in his driveway. Somebody was physically moving their home. You ever seen that, with the home literally on the trailer? And they started doing the day before, and they parked the house in front of his driveway. And they left it there for like 4 days. It started on a Friday, and they left it. So he couldn't make it to class because there was a house in his driveway. I thought that's one of the best excuses I've ever heard. But he sent me the picture, so it was, things happen, like I said, so that's always a good idea to protect yourself. Now, today what we're going to start with is surfaces generally that involve 3 variables. So now you have stuff going on, and the simplest surface you can think of that involves 3 variables is usually something like a sphere. Because you can all picture a sphere, but I need an x squared, a y squared, and a z squared to have a sphere. So in general, how do I figure out what something is if I don't know what it, I don't have the equation memorized? Well, first thing is, do not memorize. Do not memorize equations. I see people try to do everything under the sun. They'll say, well, if it looks like this, then it's this shape. If it looks like this, then it's this shape. But for every equation there's an infinite number of variations of that equation. And you're not going to memorize all the variations. So I'm going to start real simple. Okay? Let's start with something like this. I've got 3x squared, let's say, minus 2y squared plus z equals 12. Okay? Just something generic and random. But the thing is, what we're going to do, we will not use exponents other than 1 and 2 in general for this part, because if it gets too complicated, there's no possibility that you're going to know what it looks like. I won't know what it looks like. And generally speaking, you're not going to work with shapes that have higher exponents or more complicated things. That's probably something you're going to have to use computer software on, and you're probably not going to be able to give an actual answer, just some computer-generated approximation. We're going to stay away from that because there's no understanding there. I can always ask the computer to do the problem, but if I can do the problem myself and understand what's going on, way, way better. So I want to know what this is, but I'm not going to memorize the form. What I'm going to do is look at the cross-sections. So I have a 3-dimensional object out here in space, and what I mean by the cross-sections, okay, if that's the x-axis, that's the y-axis, and that's the z-axis, I want to take a slice this way, so now I'm looking at it in the xz direction. I want to take a slice this way, so I'm looking at it in the yz direction. I'm going to take a slice this way, so I'm looking at it in the xy direction. I want to look at each of the cross sections. Now, yesterday when we talked about cylindrical surfaces, the nice thing is all of the cross sections were congruent. You always got the same shape, doesn't matter where you are. Okay? Now, the first error that I see people do, because I've actually seen this in textbooks, they'll say, well, I'm going to find a cross section by setting one of the variables equal to 0. Don't do that because it won't work 99.97% of the time. And in fact, at least half the time, all of your cross-sections will now be imaginary. Never set a variable equal to a number. That will not give you a shape. And again, most of the time, you'll actually get an impossible contradiction. And I'll have people do this, they'll say, there's no shape, there's no shape, there's no shape, and here's what it is in the end. And no. You set your variable equal to a constant. And say, now what does it look like in the xy plane, the xz plane, the yz plane? So it's very, very simple. The process is exactly the same for all problems where I have three variables. So I'm going to look at the cross sections. The order is not really that important. And what I'm going to do is the other variable I'm going to set equal to a constant. I'm not going to set it equal to 0 because once again, if I set it equal to 0, I may end up getting something like something squared equals a negative number. That's going to be the most common thing you're going to see. And you're going to go, why isn't that working? So if I set z equal to a constant, then I have 3x squared minus 2y squared plus k. So why don't I just say equals 12 minus k? I set z equal to k. Now, in the xy plane, this is a scalar. There's no z. I don't simply move z to the other side. If I simply move z to the other side, I still have three variables. That's not a cross-section. It's a cross-section by taking one of my variables and setting it equal to a constant. Now, in the xy plane, I have a difference of squares. What is that?
Hyperbola.
Hyperbola. Good. That's all I need to know. It's a hyperbola. So if I have this three-dimensional object, then all slices parallel to the xy plane, that's what it basically is saying. All slices are going to look like hyperbolas. Not a particular hyperbola, they're just hyperbolas. Now, the xz plane, so now I'm going to have y be a constant. So now I'm going to have 3x squared plus z, and I'll go and throw that on the other side, equals 12 plus 2k squared. I have one squared variable and one not squared. Parabola. Good. Do I have to know what this parabola looks like exactly, and do I need to draw it in that plane? Nope. I just need to identify it. Yeah, you don't want to make this more complicated than you need to. All you're doing is identifying the cross-section. Now, in the yz plane, that means I'm going to have x equal a constant. So I'll have negative 2y squared plus z. I'll throw that over, equals 12 minus 3k squared. Again, it would be a parabola, wouldn't it? Okay, so I have my three cross sections. I can now name my shape. So what, generally speaking, because we're dealing with conics primarily, you're going to see conics, but you're usually going to see one of the conics happen at least 2 times. Right? You're rarely going to see the same thing 3 times, but that's possible. Okay? I have a hyperbola, parabola is my conics. The one that occurs most wins. And when you win, you get the title oid. So someone asked yesterday about paraboloids. This is a paraboloid. Do you know what the suffix oid literally translates to? Like. L-I-K-E. In other words, it's parabola-like. So it's a paraboloid. But what kind of paraboloid is it? A hyperbolic paraboloid. Because there are other types of paraboloids. We did that bullet shape the other day. That was called a circular paraboloid. Okay, so the name of my shape is a hyperbolic paraboloid. And it's always kind of funny, oid. That sounds like a made-up term, but no, it just means it's parabola-like. Now, this shape particularly is fun to study. We're actually going to spend a lot of time on things of this nature much later on, because it is, in terms of three-dimensional shapes, it is pure evil. Which makes it so much fun. I mean, come on, you always root for the, you rooted for Darth Vader, right? Yeah, I mean, everybody likes the bad guys. So this is probably the most evil shape that you're ever going to study. And I'll give you a really loose picture of what it looks like. What does that kind of look like to you? Kind of looks like a saddle. Yeah, so we actually refer to this generally as it's a saddle. A hyperbolic parabola looks like a saddle. Well, why would that be evil? Because depending on your point of view. Now, if you've ever seen a saddle, you've seen a horse with a saddle. We consider this, by the way, one of the most important shapes we study. We're not going to do anything with it for a couple of weeks. We just want to identify it. But what makes it interesting, when you're looking at the horse, you know, that looks like a minimum, doesn't it? When I'm staring at the horse, that looks like the minimum. But all of these guys are downwards opening parabolas. So if I'm standing behind the horse, and let's say I have a see-through horse. Okay, I have a glass horse. How's that? You know, it's it's one that goes up and down with a pole, and you know, like a merry-go-round horse. And now I'm looking at it, and I'm looking at it from this point of view. What am I seeing? I'm seeing the top of the parabola. So if I'm behind the horse looking at the saddle, I see a maximum. When I'm standing from the side and looking at the saddle, I see a minimum. That's interesting. Which is it? It's neither. It turns out it's one of the most important results that we will see in three-dimensional geometry. This point right here, it's confounding because from one point of view it looks like a maximum, from another point of view it looks like a minimum, and we don't know what to do with it. So like I said, we're going to study it later, but we have a really clever name for this point. It's called a saddle point. And it is probably the single most important result of a particular type of point. And it's not complicated, but it starts with understanding kind of what the picture looks like. You're never going to have to draw this, don't worry. But by the way, does anybody have or has anybody looked at the textbook? I know you showed me yours yesterday. You looked at the textbook at some of the shapes. It would be a really good idea, and you can look at any book online. When you look at some of the shapes, don't go by my renderings, please. Go by the ones in the textbook because they're computer-generated renderings with shading, and you know, you can see it and go, okay, that's what that thing looks like. I mean, I'm just doing my best, but the pictures in the textbooks are usually really, really good. I mean, they might not have a great explanation, but the graphics are awesome. So we just did a simple problem here. It's not the only one, but it's certainly interesting. Let's try another one. How about I have something like this? I've got about 2x squared plus 4y squared minus 3z squared equals, and I'll use 1. 1's easy enough. Okay? Now I changed something. It doesn't matter where the pluses and the minuses are. It doesn't matter where the squareds are. I just look at the cross sections and I see what I see. Okay? I gave you all squareds this time, so it's probably not going to be the same cross sections. Do you agree? Probably something's going to be different. What am I probably not going to have as a cross section now?
Parabola.
Probably not going to have a parabola because I don't have any things to the first tower. Okay. So in the xy plane, I set z equal to k, and I typically like throwing the other guy, I like throwing it on the other side of the equal sign because I think it's a little bit easier to read, right? If I have a constant on each side of the equal sign, sometimes that's kind of confusing. So this would equal 1 plus 3k squared. I have a sum of squares with different coefficients. What is that?
Ellipse.
That's an ellipse. Is it a circle?
No.
Why is it not a circle?
Coefficients. The coefficients are different.
Because the coefficients are different. If the coefficients were the same, then we'd say it's a circle. By the way, if something's a circle, don't say ellipse, because when you say ellipse, you're very specifically saying it's an ellipse, but it's not a circle. That would be kind of like saying, I'm going to give you a square, but you're going to call it a rectangle. All rectangles are not squares, but all squares are rectangles. If it's a square, you'd say it's square because you'd want to be more specific. Because if I said rectangle, you're not thinking square. Because otherwise I would have said square. That's clearly an ellipse and not a circle, but if they were the same coefficients, you want to say circle. Does that have a huge bearing on the shape? No. No, but I still want to be more accurate. So xz, so now I'd have 2x squared minus 3z squared equals 1 minus 4k squared. Now, the quantity on the right side of the equal sign, for a large value of k, the quantity on the right side is negative, isn't it? For a very small value of k, the quantity on the right side is positive. Is that an issue since this is a difference of squares? Does it matter if that's positive or negative? You remember when you were doing hyperbolas, you had x squared minus y squared, and then you had a negative on the other side? Okay, so you just switched the order of subtraction so that it was positive. It doesn't change anything. This is still a hyperbola. It doesn't matter if this is positive or negative. Okay? Would it ever matter? Yeah. And that will be our next example. A sum of squares cannot be negative, ever. A difference of squares can always be negative. There's no problem with a difference of squares being negative, but a sum of squares could not be negative. And so probably the only time you have to think about, is if I had a sum of squares, which I don't there. I have a sum of squares here. If this quantity on the right side were negative, we would have a problem. Do you agree? Because that would mean the only points are imaginary. That's not going to happen. Yeah, Joe?
So your sum of squares, if it's negative, it's a hyperbola, but if it's...
No, if you have a sum of squares, it's impossible to equal a negative number. That would mean all of your x and y's are imaginary numbers. If you find that happens and something went terribly wrong, does that ever happen? Yeah, actually a ridiculous percentage of the time, all of the answers I get are like that because people replace variables with 0. And when you replace variables with 0, you often get something goofy. Now, I have a sum of squares equals a positive number, that's an ellipse. I have a difference of squares, doesn't matter what it equals, that's a hyperbola, because it's a difference of squares. It has nothing to do with the right side, it has only to do with the left side, in terms of it being an ellipse versus hyperbola. Does that help?
Yeah, sorry, what's the difference of squares? Like, I know it's a basic question.
I have 2 squares and I have a difference.
Got it.
And this one is 2 squares with a sum. Sums of squares we know are circles and ellipses. Difference of squares we know are hyperbolas. And when there's only one square, we know that's a parabola. That was what we kind of reviewed yesterday, if you remember. Now, yz. So I have 4y squared minus 3z squared equals 1 minus 2k squared. And again, that is a hyperbola. All right. Anybody want to take a chance here and name this thing?
Elliptic hyperboloid.
What's the first word again?
Elliptical.
Elliptical, yeah. It's otherwise sounds like a cryptic hyperbole. Elliptical. So this would be an elliptical hyperboloid. Okay. Now, what exactly is an elliptical hyperboloid? Well, the ellipse right now is in the xy plane. I'm going to make a really sad attempt at drawing this thing, kind of help you understand what it is. See these cross sections parallel to the xy plane? Those are all ellipses. The cross sections parallel to the other planes are all hyperbolas. I think the easiest way to describe this, I always like to say, you're out on the farm and you got the bale of hay. You know, all the hay is going in the same direction. But to pick up the bale of hay, you've got to put a cord around the middle of the hay. And what are you going to do with that cord? You're going to cinch it really tight. So where's the most narrow place in the bale of hay? Would be right in the middle. So the bale of hay is going to kind of go like this, isn't it? Does everyone kind of get a mental picture of that? That's kind of what this is. It's hyperbolic. I didn't give it much of a bend, but it's hyperbolic this way, elliptical this way. Another one, which actually may be a more accurate one, but it's sort of archaic, it's a gurgle. Does anyone here know what a gurgle is? I found last semester was the first time I ever had a class where people actually didn't know what a girdle was. A girdle is something that women used to wear like in the 1800s and 1900s, and it squeezed you. I know this.
So like a corset.
Because I had, a corset. I had to wear one last summer. I had a couple. I have frequent flyer mileage for surgeries. I've had quite a few, and I had a surgery last summer, and I had to wear literally a girdle for a couple weeks, and it was so tight I could hardly breathe. And now I know why people complained for many years about having to wear one. It squeezes so tight in the middle you can't breathe. But it literally was that same shape, identical shape. They didn't call it a girdle at the doctor's office. They said, we're going to fit you with an elliptical hyperboloid. You know. No, actually the doctor called it a girdle. So that's what that guy is. Now, I'm going to do a version of this. I have a sum of squares equals a positive number. That's obviously always positive. And then over here, I've got these guys. I'm going to tweak this one slightly because this actually has more to the name than I gave it. There's a little bit more to the name. We're halfway through the name. I'm going to do I'll do a slightly different one this time. Let's do, how about 4x squared minus y squared minus z squared equals, let's just say equals, how about 16? I want it to be a little bit different each time we do it. Okay? Now, you suspect you're going to see a lot of the same stuff. Agreed? So when I do this, again, I have my xy, I have my xz, I have my yz. Okay? In the xy plane, I've got 4x squared minus y squared equals 16 plus k squared. The nice thing about these types of problems is because we're generally concentrating on conics, if you can remember what the form of a conic is, you can fly through these problems. So what is this guy? It's a hyperbola. Okay? In the xz, I have 4x squared minus z squared equals 16 plus k squared. Oh, that's almost an identical. So that's obviously a hyperbola. And in the yz plane, I have negative y squared minus z squared equals 16 minus 4k squared. That's kind of a problem. What is that? It actually isn't anything yet. Anybody got any ideas?
Pull out a negative.
Yeah.
Or rather than factor, how about just multiply? Oh, what if I multiplied both sides by -1? Which would have been the equivalent of just throwing those guys over and moving the 16. Oh, y squared plus z squared equals 4k squared minus 16. Oh, that makes a little more sense, doesn't it? So what is that guy?
Circle.
So this one I can say is a circle. Okay? Wait a minute, what if? By the way, this is one of the reasons you never replace a variable with 0. See, I can't tell you how many times I'll have people do this problem. They'll replace the variable with 0 and say, okay, I have negative y squared minus z squared equals positive 16, which means all my coordinates are imaginary. Do you agree? That's not possible. Well, what if I just do this? Well, now I have y squared plus z squared equals negative 16, which is equally terrible. No, it's got to equal this, but I have a problem. If k is small, this no work. You all agree? So off to the side, tell me about 4k squared minus 16. It's got to be,
Greater than 0.
or
Equal.
you all agree? It's got to be greater than or equal to 0. Oh, that would mean 4k squared is greater than or equal to 16, so k squared is greater than or equal to 4. So the absolute value of k is greater than or equal to 2. Does that change things? That changes things hugely. This doesn't look anything like the previous one. Oh, because this one has restrictions. That's what I was referring to earlier. When you have a sum of squares can never be negative. A sum of squares can be 0, that's not a problem. That just means you have zeros. So what this one's going to look like, okay, I have hyperbolas in the xy and xz, and I have circles in the yz. Okay, so that's kind of weird. I have circles in the yz. Let's see, the yz. I can do this accurately. It's going to look something like this. By the way, this is infinite. And there's a gap. How big is that gap?
4.
4. Yeah. 4.
2. There's a gap of 2 units because I gotta be past that. So this is kind of like my bale of hay. It's kind of like my bale of hay. But imagine I did the bale of hay and I kept cinching it so tight it eventually snapped. And now I have 2 completely separate pieces. Now they're both circular hyperboloids. So this is still a circular hyperboloid. But the first one was 1 continuous solid object. This is 2. So the first one was called, it was an elliptical hyperboloid, correct? Elliptical hyperboloid of 1 sheet. That's the language we use. So this one is a circular hyperboloid of 2 sheets. This is one of the only times you ever have to consider restrictions. Again, if I have a difference of squares or I have something that's parabolic, anything can be negative. That's not even an issue. It's only a sum of squares that cannot be negative. Because then again, you'd have imaginary coordinates. A sum of squares cannot be negative. And when I looked at this, hey, are there values of k that would cause this to be negative? Yes. So I had to set it up so that the absolute value of k has to be greater than or equal to 2 for me to do this. Now, in my picture, remember the x-axis is coming out at you. So in the yz plane, remember we replaced x with a constant. So in English you can say, oh, all of my x coordinates would have to be greater than or equal to 2 or more negative than negative 2 for this to work. Does that make sense? That's why there's a gap here of at least 2 units and then it starts in both directions. Again, you don't have to draw it, but if you look in your textbooks or you look online, you'll see a picture like this. The equations themselves looked very similar, didn't it? I had all 3 numbers be squares, and they were not all the same signs. Okay? And you go, oh, okay. So now when I'm looking at my cross sections, it's possible that I might have restrictions. You don't have restrictions that often, but it is possible. Okay? So that's probably the most, I don't want to say the most complicated, but probably the one that requires the most thought, because I have to consider that. In none of the other ones that we did was that an issue. Okay? Now, there's one more that comes up often, and it's a fairly simple one. I like this one. It's z squared equals x squared plus y squared. I'm going to write it in that form, because this one we actually use quite often, and a lot of folks, they get confused on this one because it looks very different from the other ones. And so, the lack of any constant terms means that, yes, my variables can be 0. For example, is this going to pass through the origin? Yeah, if x, y, and z are all 0, yeah, it passes through the origin. This one turns out to be hugely important, and I'll go through as to why in a moment. Actually, it should be dotted. What does that look like to you? Okay, hourglass. It's another shape. What are all of our cross sections so far? They're called conic sections.
Yeah, it's kind
Where do they all come from? It's a cone. Conic sections come from this guy right here. This is actually, sort of like the grandfather of conics. They all come from here. Okay, so in this case here, and this is an easier way to think about it. I said in general, you can't just arbitrarily set a variable equal to 0 in general because you can get imaginary coordinates. But in this case here, it's easier to discover what this looks like if I actually do say, what does it look like on each plane? So, for example, if I said, the plane that you're looking at on the board, that's z and that's y, so that's the yz plane. If x were 0, then I have z squared equals y squared, which is the same as saying z equals plus or minus the absolute value of y, which would be those 2 lines. Now, if I'm looking at it this way, I could say z equals plus or minus, well, by saying plus or minus absolute value, it's just plus or minus. So plus or minus x, which would be this way. And if I let z be any scalar, positive or negative, then I have x squared plus y squared equals number squared, which is a circle when I'm looking down. So what you're doing now is you're standing on the top of the z-axis. We do a lot of that in this class, by the way. We stand on the top of the z-axis, we look down, and what do you see when you're standing on top of z?
Circle.
You see circles. So this one's a little bit different from the other ones because this is the only one that we generally look at that doesn't have a constant term. And so it actually makes it a little bit easier to discuss. Okay, so this is a circular cone. If I put coefficients on either one of these guys, then those would be elliptical cross sections, wouldn't they? So they'd be elliptical cones. Cone, like cylinder, a lot of people automatically assume circles because that's the most common version we use, but it doesn't have to be. Now, what if I only wanted the top half? Is there a way to write this where I only have the top half? And we do a lot of this also in this course. Right now, z can be negative, can't it?
Absolute value.
Not absolute value. Actually, back up one step. If I said solve for z, wouldn't you say plus or minus? So what if I just said z is the square root? Then it's the top half because there's no negatives. If I do the plus or minus, then I get the bottom halves. So this would be the top half of the cone. This would be both halves of the cone. And there's a common error that occurs that people look at that and they interpret whatever the other one is. Yeah.
Would that be one sheet or two sheets?
No, you just call this a circular cone.
Okay.
And by the way, the 1 or 2 sheets is because there's actually a break. There's technically not a break because there are no places where I can't use a value. See, in this example over here, I cannot have any x values between -2 and +2. Does everybody understand that? There's no x values between -2 and +2, so there's a clear break in the graph. But there's actually no restriction on the x's and y's in this case. That's a good question. Restrictions are the one thing we hate because you have to think about it. but there's really nothing about this that is truly complicated. It's all identification and identification only. That's it. So you don't have to get clever with this at all. Do a simple example. If I gave you a sphere, let's do a simple sphere. Okay, I got a sphere centered at the origin. Okay. Okay, so I've got x squared plus y squared plus z squared equals rho squared. If I have any of the variables equal to 0, that's called a trace of the graph. A trace would be the equivalent of a projection onto a plane because you've set one of the variables equal to 0. And many graphs have traces, but not all graphs have. That graph didn't have a trace. Oh, see, the problem with setting a variable equal to 0, it only works if the graph actually intersects the plane, the xy, xz, or yz plane. This graph obviously intersects all the planes, and the intersections look like circles, which is very nice, isn't it? Do you all agree that that's a nice thing? So let me change the problem, just ever so slightly. Just to illustrate why we do things a certain way. I have the same sphere. So now what's the equation of my sphere? Now, in my picture, my sphere does not intersect any of the planes. Agreed? It's just out there in space. If it helps, think of it this way. Think of, I have it in the first octant. Think of x naught, y naught, and z naught as being fairly large numbers. Three large positive numbers, and think of rho as being a small positive number. So in other words, the center is much further away than the value of rho. So this might be 10, 10, 10, and rho is 5. So I'm just out there. But there's no trace now because it doesn't intersect the plane. So if I replaced any of the variables with 0, I would get all imaginary coordinates again. So that's why you don't replace a variable with 0, you replace a variable with a constant. And then you ask the question, are there restrictions on that constant? Most of the time there are not. Okay, so I want to illustrate the difference. We don't deal with traces very often in this class, and that's actually a specific word, but we do a lot of stuff with what are called projections. which is a little bit different. If I want to project something onto a plane, okay, so now if I said I want to project this, does this intersect the XY plane at all? No. But if I'm standing up on top of the z-axis and I look down, what do I see on the XY plane? Don't I see the image of this circle? Think of it as the shadow. Do I see the shadow of this sphere looking like a circle on the XY plane? Does everybody see that? That's a projection. But it never intersects the XY plane, so there is no trace. Many of the textbooks have you using traces to figure out the cross sections. That's incorrect mathematics. Why? Because it doesn't work all the time. It only works some of the time. Okay? It worked on some of the problems we did today. It doesn't work on all the problems. And it definitely didn't work on the cone. Do you realize if you use that for the cone, then you're going to say the entire shape is the origin, and that's it. You only get the origin as an example. You say, how come? Because if x squared plus y squared equals 0, that means 0, 0 is the only point you get. You can't get a shape from a point. So that's what it is. There's no calculus in this. It's identification of two-dimensional shapes, which is a lot easier than looking at the three. Yeah, Liam.
I don't know how prevalent this question is. Typically when you handle quadrants, you go 1, 2, 3, 4. How do you count the octaves?
Oh, that's a great question. It's actually the same.
Okay.
I used a term that some of you are not familiar with. How many have heard the term octant? In the XY, I'm glad you brought that up. In the XY plane, we have 4 quadrants, because quad means 4, because there's only 4 choices, right? I have plus, 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 minus, minus, plus, minus, minus as my ordered pairs. But when I throw in the third coordinate, I have 2 choices for the first, 2 choices for the second. So I can go plus, 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 minus, plus, minus, plus, plus, minus, minus. I have 8 different choices. So that's why they're called octants, because that's 8. If that is the origin, and that is the positive x, the positive y, and the positive z, then where are we?
First octant?
We're in the first octant. And most of the time, we don't really worry. So the second octant would be if I make only the x negative.
Okay.
Does that make sense?
Yeah.
I don't ever want you to worry about that, though. That is a great question. But now I'm trying to rely on the fact that I can now see. You see, what's on the other side of this wall if we're in the first octant? So again, it kind of depends on you. Well, how am I looking at it? Well, that's probably the second, that's probably the third, that's probably the fourth, and what about underneath us? 5, 6, 7, and 8. Never worry about that. To me, that's way too confusing. But what you're going to have is a lot of application problems that we're going to do later, where we'll say we have a shape and it is bound in the first octant, and that makes it so much easier to conceptualize. One of the most common ones we will deal with is I'll have a plane cutting through and bounded in the first octant. And I'm going to give you a picture. This is probably, for applications, of which we do a lot, this will probably be one of the most common applications, not because it's easy. No. It isn't necessarily easy, but from a conceptual standpoint. I'm going to do a really simple plane because we've been practicing planes. You really should be able to draw a plane. Wait, how do I draw a 3-dimensional linear thing? Oh my gosh. Well, I'll do one. So I've got, how about 3x plus 4y plus 2z equals 12. There's a plane. I'm going to show you how to draw a plane. But I particularly chose all my coefficients to be positive. That makes it a little bit easier for me to do this. Now, 4, 0, 0, or 4, 0, 0. Is that a point on my plane? So I'm going to go out 4 units. All right. How about 0, 3, 0? Is that also a point on my plane?
Yeah.
And how about 0, 0, 6? Is that a point on my plane? 4, 5, 6. All right. There's my plane. If you need to do those, Planes go forever, but I've written enough of the plane that you can tell where it is. When you draw a line on the XY plane, don't you only do a short line segment and then put arrows on the end? I mean, you don't draw forever. I mean, you draw enough of the line that anybody looking at it can tell, okay, there's where the line is. Can everyone see that this is where the plane is? It's cutting through the first octant, and these are the particular intercepts. Now, This was not rocket science. This was not even difficult for me. But now you have a simple illustration of what a plane looks like. So a question that we're going to do, maybe, I say, what is the volume enclosed in the first octant? Or tell me about the vector that describes the normal vector to the plane. That will be something that's not very complicated later on. There's a bunch of questions I could ask in this case. But it helps to know what the shape looks like, first of all. Now, if I'm bounded by we say the coordinate planes, not the axes, we're bounded by the coordinate planes, then what is the shape that I've created? Does anyone know what that's called? By the way, it is triangular pyramid is a correct name, but there's a much more specific name. It's considered the simplest three-dimensional shape there is. In 2 dimensions, right, one line passes through 2 points, so a line segment is the simplest one-dimensional shape. In 2 dimensions, if I give you 3 distinct points, a triangle is considered the simplest two-dimensional shape because I only need 3 distinct points. How many points do I need to describe this shape? 4. So this has 4 vertices. And what's Latin for 4? There's another one besides quad. Tetra. Tetrahedron. Should you know that? It would be useful. We will use that term fairly often in this class. Tetrahedron is the simplest three-dimensional shape there is because I only need 4 points to describe it. Cool.
I thought this was a plane.
Well, no, I said what is the thing that I've enclosed? I said I'm bounded by the coordinate.
Okay.
I said if I'm bounded by the coordinate planes, what's the three-dimensional shape that I've enclosed? Yes, so I have a bunch of planes, but notice there's only 4 vertices in this. So it's useful to know that because it's a vocab term. There will be a lot of vocabulary in this course that is geometric vocabulary. So it's stuff that very likely you were exposed to, and I use the word exposed. Does that mean you know it today? Not necessarily. So I will constantly be reviewing vocab because it's necessary. We all know this when it comes to vocab. You can understand everything that went on in a lecture. But if the instructor uses even one word that you don't know what it means, do you really understand the lecture? No, you're hoping, but you're going, I don't know what that word meant, so I don't know if I've interpreted any of it correctly. And I say that in all seriousness. If you're weak in vocabulary, it's really hard to get the big picture because the vocab sometimes explains everything. And I tell a funny story that I think it's a funny story. Several years ago, I went back to school. I was kind of bored. I teach my normal day here, and then I went to San Diego State in the evenings and afternoons to take the statistics program. And then I took the last semester off to finish the master's program. I took a sabbatical. Greatest thing ever. It's where they pay me my full-time salary to move all the way up on the pay scale when I'm all done. Yeah, it's a good gig if you can get it. That was about, I think that was 2007 that I did that. But I went for 5 years. The gnarliest class, non-parametric statistical methods. It was considered the hardest class at San Diego State, not in the stats department, but at San Diego State. And in the stats department, it was an elective for the graduate degrees. So people avoided it like the plague. But the instructor I knew very well, and I'd had several classes with him, Dr. Liu. He was the second most published statistics person on planet Earth at the time of his passing a few years ago. And he taught this class. And one day he's talking about a problem, and a statistical method, and he's talking about all the different variables, and he kept saying, we need a parsimonious variable to do the following. And he kept saying that. And all I could think of is that creepy little orange fruit that my grandfather used to pick when we were little, persimmon. I'm like, parsimonious. I have absolutely no idea. By the way, I have asked every student I've ever taught, and I have not had one human being actually tell me they have any idea what it means, and it's okay. I'm sitting there through the gnarliest graduate course, and I have no idea what the heck he's talking about. And everybody else in the course, well, most of them were all PhDs in health science. They're like, yep, And I'm sitting there going, I have no idea what's going on. So I went home. I Googled parsimonious. Do you know what parsimonious means? Stingy. Stingy? That's the first definition that came up, and then I started doing a little more research. In the statistical process, especially if you're a statistician, you want variables that require the least amount of information in order to perform your task, because it makes your task easier if you don't have to gather a lot of information. So you want a variable that requires the least. In other words, you want a variable that is stingy. So the next class occurs. Okay, it's 2 classes a week. And he's going through a whole process, and what do we need to do? And at this point I said, oh, at this point we need to select a parsimonious variable so we can finish blah, 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 blah. No joke, there's like 18, 20 people in the class. It was dead silence. And I actually could hear in the background, he said the word. Class ends, Dr. Lou leaves, literally 5, 6 people run to the door, close the door and sort of barricade the door and say, could you please explain to us what all of that meant? The previous class, I felt like a complete idiot because everybody else in the class is yep, got this. And I have no idea what's going on, so I figured out what was going on. Nobody else did. So they pretended for an entire week to know what was going on. And by the way, several of these, he only gave a midterm and a final. He was a great professor, but not a great organizer. He gave a midterm and a final. About half the students failed the final. And you can't get a C in grad school. You definitely can't, which meant they were kicked out of the program. All because their egos were so big they couldn't ask a question or find out. Well, the point was is that one word stumped me. I didn't know what the heck was going on. And once I understood the word, I knew everything that was going on. And I actually got 100% on both the midterm and the final in the class, by the way. Because he gave tests on stuff that he taught in theory. It was all proofs and theories, but still, if I say a word you don't know what it means, it is totally okay to raise your hand because you know the absolute rule. That if you don't know what it means, it's probably safe to say half the people in the class don't know what it means. You're just the only one smart enough to ask. And so I always maintain you have to be selfish in a classroom, right? Samuel should never let me go on if he's not sure what's going on. That's why I always sit in the front row. I'll have a dialogue with the teacher. Okay, well now why are we doing that and this? It's okay to do that. Because if you don't understand what's going on, then you're wasting 2 hours and you're gonna have to figure it out later. And I don't want you to figure it out. I just did something that was not complicated in any way, but it's nothing like anything you've seen in identifying things. Do exactly the way I showed you. Don't make it more complicated, and please don't go somewhere else. That's the one thing that drives me crazy as a math instructor, when people will go somewhere else after I show them how to do it, they go somewhere else to get it. And by the way, if it doesn't match what I said verbatim, then I guarantee you it's 100% incorrect. Because what I showed you is the only way that exists to do it, and it's not that complicated. It really isn't that complicated. So, you know, you say, oh, okay, now we're going to completely change gears because now we're going to talk about motion. Now, this is a little confusing from the standpoint of trying to represent graphically. I can draw a picture of a surface. Okay, I've done a fairly decent job. You guys kind of could tell what I was talking about. If I have an XY plane and I give you a function, I can draw the curve fairly accurately, or if I can't, I'll just bring it up on Desmos, right? I can show you exactly what the curve is supposed to look like. Here's what I want to do. I'm going to put a little sensor on the tip of my finger, and I'm going to excite the room with particles, so as I move through, you'll be able to see. Can everybody see the curve that I'm creating right now? You can all see it, right? Piece of cake. You see this curve through space. Now, I'd like you to draw it on your paper. Will that work? Can you draw a three-dimensional curve on a two-dimensional surface? No. Can I have a computer do it? No, because you have no depth perception. You can't do motion in 3 dimensions on a 2-dimensional surface. In fact, better yet, what if the motion's coming straight at you? Then you're going to look at a dot that doesn't move, right? So I need to describe this motion because motion is one of the most important things we're going to discuss in this course, and it's all we're going to do the next few days. Whew, that's tough. I can't draw a picture, and there is no equation for a function. Excuse me, for motion. There's an equation for a surface. There's not an equation for the motion, so that makes it a little bit tricky. The simplest analogy I can come up with is a harp. Does anyone know what a harp looks like? It's huge and it's got all those strings of varying lengths. Imagine your motion was the outer portion of the harp for a moment. And then I want you to imagine all the strings of the harp to be a vector. So here's the thing. I have a curve and I'm going to move through space. At, let's say, time 0, I'm here. I want to draw a vector from there to this point. Now, 1 second later, I'm here, so I want to draw that vector. 1 second later, I'm here, so draw that vector, and so on. What are you going to see after a while? It's kind of the idea of the harp, isn't it? I used to use sometimes I use the analogy of nails. You know, the nail board, when you put your face in and it carves out your picture in nails. Well, I want to do that, but I want it to be more 2-dimensional. So the curve. So as I'm moving through space, every point on my curve, you have a vector going back to the origin. Can you all kind of see that mentally? You have a vector going back to the origin. The point on the curve is the terminal point of the vector. So this is the one time where points and vectors kind of overlap. A vector is a physical thing that has magnitude and direction. A point is an address. It has no value. It can't be combined with anything else. But if I describe my position in space always as the terminal point of a vector, then I can use the vector to describe my motion. And this is called a vector valued curve. Okay? In 2 dimensions, this would be very, very simple. So let me start with a 2-dimensional analogy. Okay? I've got y equals f of x. And let's say y equals f of x, you know, maybe it looks like this, okay? It's something like that. Could I simply go like this? I want to describe my motion as the terminal points of vectors. Then that means that I need to have a vector that always gives me those coordinates. So here's where we use a parameter. Now remember, a parameter is a variable external to the problem that you can use to describe the problem. Back in Calc 2, you did parametric equations and parametric derivatives, and remember doing that? Hopefully you did that at the very end of your Calc 2. That was the last thing you did. So if I used a parameter, then I could describe shapes, and not necessarily things that were even functions, right? A circle was real easy because I used cos t and sin t. Oh yeah, okay. So if I did something like this, if I said let x equal t, and then y be f of t, then this will always be t comma f of t, every point. And we usually call the vector valued function r of t. So in this case, r of t, which would be x of t comma y of t, well in this case x of t would just be t, and y would be f of t. I can describe my 2-dimensional motion this way. Now, this is a little overkill because I already know how to do it. Right? It's much easier if I just use a function. But what if I had something like a circle? I want to take something that's not a function. In fact, let me use a simple one. Let's suppose I have a circle. We have the following circle, x squared plus y squared equals, let's say, a squared. A is just some positive number. You cannot solve explicitly for x or y because that's not a function. But I can parameterize that. And so what you did, hopefully, when I say hopefully, I'm thinking, you know, that's what you're supposed to do in a Calc 2, and my hope is that your Calc 2 did what they were supposed to do. You would say let x equal a cos t, and let y equal a sine t, and then if you do a quick check, then x squared plus y squared will in fact be a squared. Okay, so when t is 0, I'm here. When t is pi over 2, I'm here, pi, and so on. I would then describe this whole circle, and all I have to do is have my t range from 0 to 2 pi. So this would be a parameterization of this circle. But what if I wanted a vector-valued function to represent the circle? Okay, this is what's new. What I'm showing you there is something that's in your Calc 2 book, and hopefully in your Calc 2 course. And I say that in all seriousness because I wrote the curriculum that the district has to follow according to the state of California. And this is the last part of almost every Calc 2 course. You probably didn't do it early because the calculus books is usually the last chapter. And so I say, I wrote the curriculum, I actually did. Every single topic that has to be covered in Calc 1, 2, and 3, I'm the one that did this years ago. I decided if it doesn't get covered, we have issues. Mostly lack of preparation for the next class, or we've had instructors only cover half the material, and you know that's a problem because technically the course can't count according to the state. Yeah, all sorts of bad things happen when people skip, but we can always fill in the blanks.
For the whole state?
No, the state of California has requirements, and the districts have to follow them.
Oh, the district, okay.
Yeah, the thing is that it's not Calc 1 has to cover this, Calc 2 has to cover this, Calc 3, it's Calc 1, 2, and 3 has to cover this. Did anybody take Calc 1 or 2 at a different school? This is always an issue. This happened to me. This happened to me. I took Calc 1 at one school and then switched and took Calc 2 at a different school. And the first 2 weeks of Calc 2, like, this is awesome. I already know this stuff. This is gonna be the easiest course ever. And after 2 weeks, it dawned on me, okay, I'm at a different school. Maybe they did things in a different order. And if I've seen everything they just showed in the first 2 weeks, because I did it in my Calc 1, then there must be something they did in their Calc 1 that I didn't do. And that's exactly what happened. And I had to teach myself the next like 3 weeks, because I wasn't at the top of the class. At that point, I was now at the bottom of the class because I didn't see any of that, because schools don't have to cover the same thing per class. They have to cover everything per sequence. Does that make sense? That's why, by the way, that's why most universities, if you actually go to the websites, which I did because my kids were applying, most universities, particularly like UCs, recommend that you complete sequences at the same school, at least year-long sequences. And part of the reason is because you're going from semesters to quarters, which is a terrible translation, but really the other thing is for what I'm describing. You're starting a sequence at one school, switching to another school that isn't necessarily following the same order of things. And therein lies a problem of it's very easy to miss things that way. And it's not your fault, but there will be things that get missed because that school covered it in the first semester and your next school covers it in the second, flip-flop. So if I was to describe this as a vector valued function, I would describe it this way. Now, for every value of t, when t is 0, I have exactly this vector right here. That is the vector when t equals 0. How do I know that? Because it would be a 0. Now, when t is pi over 2, I have this vector. When t is pi, I have this vector. When t is 3 pi over 2, I have this vector, and I would complete my whole circle. If I'm only looking at the terminal points of the vector, does everyone see that I will actually complete the circle? Okay. Now, is there a practicality of this? I mean, I already know it's a circle. Well, by doing it this way, I could specifically solve for x and y, which means things like derivatives might be a lot easier. In other words, I wouldn't have to do things implicitly necessarily. Okay, so this is a simple one. But mainly the reason I want to do this is because now I want to extend this into 3D. And there is no equation ever to describe a curve. There's only equations to describe surfaces. So a vector valued function will now look like this. Forevermore, this is what we're going to do. And it was pretty clever, whoever figured this out. I have x of t, y of t, z of t. There's one variable. If it helps, I always think of t as literally being time. Okay? So when I start the process, maybe t equals 0. At t equals 0, I'm right here, which is that vector. Now, at t equal 1, or it could be t equal 0.1, it could be t equal 1 million. Choose another value of t. Now maybe I'm over here. I've moved from here to here, and my vectors, right, are charting my path. Based on this, we'll be able to describe things like velocity and acceleration and curvature and all these things over the next couple days, based on the fact that I can describe things as a vector valued function. But it also means derivatives and limits and other things are actually quite simple. But you have all these variables. No, I have all these functions. I really only have one variable, t. T is the only variable. X is a function of t, y is a function of t, z is a function of t. X, y, and z are not functions of each other. Oh, so as I move through space, my position in space is entirely dependent only on t.
Would it be correct to see this as like the polar curve? Like the polar curves? Like the vector being a radius?
Well, polar curves, I can use this, but I don't have to.
Isn't it kind of the same thing though? Like the vectors, they look like the radiuses and
then... Well, in this example, yes.
Yeah.
But not necessarily in the 3D case. I used the circle specifically when that looks very polar, you're right.
Okay.
But I did this to illustrate what you can do in 2D, because now we want to go to 3D. Now, there's a couple of things we need to do. We want to be able to define limits and derivatives, because derivatives tell me things, okay? Think baby algebra. You described your position, you used a function. Then you could find arc length and different things. But you also could describe things like speed and acceleration and other things. You knew taking derivatives. right? So if I'm moving just on the xy plane, you knew the first derivative probably had something to do with speed, and the second derivative probably had something to do with acceleration, right? You did examples, you didn't spend a lot of time, because those things really are vector things, but you were exposed to things like that perhaps, okay? Think about that for a moment, right? Instantaneous rate of change per time, oh, that's, miles per hour, that kind of thing. Well, we're going to go way more into depth, but we're going to describe it this way. And all of the motion that we do will be three-dimensional. We're not going to do anything just in two. So here's the question. I want to be able to take a limit. Why? Because I want to be able to take a derivative at some point. And derivatives are limits. So a vector is a thing. A vector is not a function. It houses functions.
I think you could.
Well, there we go. So a vector is a physical thing. I can't take a limit of this desk, right? So we have to define what we want the limit to mean. So here's the way we're going to define it. We're going to say, I want the limit as t goes to, let's just say, some specific value. T naught will be a value of r of t. We're going to define it this way. And this is, I don't want to say this is an oh duh. I love oh duhs, by the way. Anytime we can have an oh duh, that's great. It's close. We're going to define the limit of a vector as actually the vector of the specific limits. Because you can't take the limit of a vector, but you can take the limit of the functions inside the vector. Does that make sense? Does it kind of ring? R is a thing. R doesn't approach anything. Oh, but since R houses these three specific functions, if I take each of these individual limits, then that result will call the limit of R. Now, you're not going to be taking limits of vectors in general, but I need the limits so I can make the derivative connection, because the definition of a derivative is a limit, okay? So if I start with this simple definition, then it turns out derivatives are not that bad. And differentiation is pretty much the main operation you're going to perform on these vectors. You're never going to integrate a vector, by the way. There's really no use for that, just derivatives. So, Calc 1. If I said y equals f of x, Calc 1, then dy dx, which we also call f prime of x, is the limit as delta x goes to 0 of delta y over delta x, which is also equal to the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. The second one is the one you're more familiar with, because every time you came up with a new derivative formula in Calc 1, remember you expanded that, you did a bunch of stuff, and came out with an answer. This is called the definition of the derivative. This is also the same thing, but you rarely get to do it in this form because you're usually doing functions, manipulating, that kind of stuff. So the derivative is defined to be a limit, right? Problem is, how do I apply that to that? Well, let's try that. I'm going to erase this for a moment. Remember, there's no division, so that kind of gives us a little bit of a problem. So let's start by defining the following. What if r of t is x of t, y of t, z of t, I'll make it easy on myself, then what is r of t plus delta t? That should make it fairly simple. What would that be? That would be x of t plus delta t, comma, y of t plus delta t, comma, z of t plus delta t. Okay? That's not calculaic at all, right? I don't have any limits or derivatives yet. So do we all agree with that statement? Next one. Then what about r of t plus delta t minus r of t? Could I write that as x of t plus delta t minus x of t, comma, y of t plus delta t minus y of t, comma, z of t plus delta t minus z of t. This is kind of long-winded, but so far so good. Again, there's no calculus yet. I haven't done anything calculated yet. I would really love to do this, but the problem is this guy. I can't divide a vector by delta t. That has no meaning mathematically, and it's even worse if I try to take a limit of delta t outside of a vector. But could I do this instead? Is that the same thing?
Yes.
Yeah, that's how I get around it. I multiply. It's like, oh, your best Napoleon Dynamite gasp. Yeah, you multiply. You don't divide, because that's not even an operation for vectors. But if I do this, last thing I want to do, I want to do this. 1 over delta t times r of t plus delta t. Hopefully you can all see where this is headed. So what is this? I want to multiply this quantity by 1 over delta t. So put the delta t inside the vector then. So what would this become? X of t plus delta t minus x of t over delta t, comma, y of t plus delta t minus y of t over delta t. Z of t plus delta t minus z of t all over delta t. Again, I haven't done any calculus yet. Got any great ideas? We want to define d dt of r of t. I want to take the derivative of this. Now there's two notations that we will use. When you did d dx of y or d dt, whatever you did, you could write it two ways. I can write this as dr dt, and notice I still use the vector notation because the derivative of a vector will still be a vector. Or I can write r prime of t. Both are acceptable, both are correct. Okay? It's kind of a context thing. You know, whatever you're doing, which one is more convenient. And we will use both. Okay? What do you think this is going to be? Well, based on the definition of the derivative, it should involve a limit, shouldn't it? So this should be the limit as delta t goes to 0 of that quantity right there. Of 1 over delta t times r of t plus delta t minus r of t. Now here's the beautiful thing. We defined the limit of the vector to be the vector of limits. Agreed? So I'm going to, rather than rewrite everything, because I'm getting tired of rewriting everything, and I know you are too. What is this? I'm going to write limit, limit, limit. Okay. Are we all good there? But that's not the final result. What is the final result then? Well, isn't this the definition of the derivative of x of t? So that means my result is dx dt, dy dt, dz dt. Because that's it. Could you write x prime of t, y prime of t, and z prime of t? Yeah. They mean the same thing. So here's the whole point. We did all of this, had to define the limit first, so the limit of a vector is the vector of limits. What have I just derived then? The derivative of the vector is the vector of derivatives. You should rejoice in that, because it didn't get weird, did it? There's not some strange rule now that you have to worry about. That's it. We have just derived that the derivative of the vector is simply the vector of derivatives. Nothing more, nothing less. And that's not terrible. That's actually really nice. And the best part about this is we can now apply these rules to dot product and cross product, by the way. They apply to dot and cross product in much the same way. In other words, we have things like product rules. We know product rule of functions. Is there a product rule for vectors? Like if I did a dot product or things like that? I mean, it seems like there should be. Do you agree that it certainly seems like there should be. So I want to do that. Because this is something we're going to use actually even today. So let me make it real simple. Let me just make up, I'm going to make up two vectors. What should I call them? How about, I'll call it f of t and g of t. And I'll just do them in R2, because whatever results we get, it's going to extend, because I want to see how would it work if I wanted to differentiate something. So if I called this one, let's say, what should we do? Let's say, how about a of t, b of t? And we'll call this one c of t, d of t. How's that? I don't want specific functions. I have these different functions. Okay, so let's first, what is f of t dotted with g of t? Let's do that first. We're going to derive a really, really powerful result in a moment. And I will leave cross product up to you. Okay, what is this? This is a of t times c of t plus b of t times d of t. Do you all agree with that? Yeah, that was pretty complicated stuff. I want to differentiate both sides now. So I now want to do the following. I would like you to differentiate that dot product. Well, I don't know how to differentiate a dot product. I have no idea. No one ever showed me that. But I can differentiate this, can't I? That's Calc 1. Does everybody see that? So I'm just going to use product rule on this. So according to the product rule, it should be first times the derivative of the second, and I'll just write c prime of t, plus the second times the derivative of the first, okay? Plus b of t d prime of t plus d of t b prime of t. All right. Well, that's really helpful. That's too much stuff going on there. Maybe. Could I maybe break this up into something smaller? Do I see any dot products or anything here? Well, I've got A and B. What if I group these two together? And what if I group these two together? Okay? I'm just going to rearrange them slightly. So I have A of t, c prime of t, plus b of t, d prime of t. That's my first matching. I see a product plus a product. Isn't that what dot products typically look like? Is it possible that this comes from a dot product? Yeah, how about a of t, b of t, dotted with what? c prime of t, d prime of t. Oh, okay. That seems kind of obvious, doesn't it? Now let's do the same thing for the second pairing. See, a lot of us are looking at these side by side and we don't see anything. Well, you're not supposed to. But if I look at this one with this one, oh, okay. So let's group the second two. So it was c of t, a prime of t, plus d of t, b prime of t. And in terms of vectors, that sure looks like it's c of t, d of t, dotted with a prime of t, b prime of t. Okay, great. Does that help me at all? Well, isn't that f of t? What's this? What is this vector very specifically? Isn't it g prime of t? I mean, look at my original definitions. So right now I have that's equal to f of t dotted with g prime of t. Now what's the second pair? Plus g of t dotted with f prime of t. Oh, my gosh, doesn't that look like product rule? Does that look like product rule of functions? So the product rule of dot product is pretty much the same as product rule of functions, except I'm not multiplying the functions, I am dotting the vectors. Is that a good thing? Yeah, it's a great thing. That means the calculus of vectors behaves just like the calculus of functions. I could tell you that, but it's much easier if I show you that. So if I have a dot product and I want to differentiate the dot product, I can actually use product rule on the dot product. Or I can multiply it out first and do it that way. Whatever's more convenient is really what it comes down to. But that's kind of a cool thing. Now, go backwards. When we did projection, when did we do that? We did that 2 days ago. I want to remind people something. If I said, okay, what is the magnitude of a vector squared?
The sum of all its components squared?
So you said, v1 squared plus v2 squared plus v3 squared under the square root, but I squared it. So it's just v1 squared, v2, v3.
Yeah.
Question. Is that the same thing? If I take a vector and I dot it with itself, what are you doing? You're squaring each component and then adding them up. Is that the same as squaring the magnitude? Yeah, that was why in the denominator of the projection function, I left it as a dot product rather than a magnitude squared because it's actually easier to conceptualize. This is always true, by the way. If vector dotted with itself is a scalar, and what scalar is it? It's actually the square of the magnitude because it's the sum of the squares without the square root. Okay? This is an important fact here. So let me suppose something. I'm gonna do something now that we're going to use next day, but next day is going to be a recorded lecture, and so I want to get this in ahead of time because this is huge in terms of describing motion and properties of motion. Okay. Suppose the magnitude of my vector is constant. C is a constant. By the way, is the magnitude of a vector constant in general if my vector has variables? No. If my vector is scalars, yes, then the magnitude is constant. That's true. One of the most common mistakes people make in Calc 1 even, I want you to take the derivative and I want you to evaluate the derivative at a number. There's an order of things you have to do. If I evaluate my function at the number and then I take the derivative, then the answer to all derivative questions is 0. And boy, that makes derivatives really easy, doesn't it? Because I just differentiated a constant. No, you take the derivative of the function, then you evaluate it. Well, the same thing is true with vectors. We often make the same mistake. I have vectors that house functions, and I'm going to evaluate them at particular values of t. T equals 0, t equals 1, t equals 2. Doesn't matter. But I'm going to also take derivatives of my vectors and evaluate them at scalars. So a common mistake is that people evaluate first, and then they take the derivative, and they always get the 0 vector. Wow, calculus is so easy. I get zeros to every answer. Well, it's because we did things in the wrong order. Okay, so I have a vector of functions. But see, that could be like sine and cosine. Oh, so when I'm finding magnitudes, I actually can get constants. It's possible to get a constant magnitude even if you have variables, particularly if you have, trig stuff. Okay, so that's not something weird. Or another easy way to think about it, I have a vector, and my vector has nothing but variables in it, but I made it into a unit vector. And what's the magnitude of a unit vector? It's always 1. Oh, so a unit vector would definitely have constant magnitude, even though I don't have constants in my vector. Okay, so I said start with this. Okay, now here's what I want to do. I want you to differentiate the, I'm using, it could use any letter of the alphabet. I want you to differentiate this. I want you to differentiate v dot v. Okay, let's do we just did this, right? This is product rule. So what's the answer? First times the derivative of the second, I'm gonna use this notation this time, just for fun. Plus the second times the derivative of the first, okay. Which, by the way, isn't this exactly just 2v dotted with dv dt? Do you agree? Because I just got the same thing twice. Does that equal something? Do I know exactly what it equals? If the magnitude of my vector is constant, then isn't this the same as asking you to differentiate what? What am I differentiating here?
Magnitude squared.
Yeah, c squared. And what must that be? Constant squared. What must this derivative be? Must be 0. The supposition I started with was, I said, suppose we have a vector of constant magnitude. Not a vector of constants, but a vector of constant magnitude. If I did a circle of radius 1, if I did any unit vector, that has constant magnitude. Okay, that's not an issue. I have variables, but I have constant magnitude. Okay, this is a very, very special case. This is not the rule in general. This was supposing this, which actually is powerful because it does happen fairly often. Okay, then if I differentiate this, which is equivalent to doing this, then I know my answer is 0. So I'm going to put the 0 here. Why is that important? V dotted with its derivative is 0. Yeah, yes. And then the max. V and its derivative are orthogonal. By the way, a vector and its derivative are not orthogonal in general. No. They have nothing to do with each other. A vector and its derivative, they're just things. But if I start with a vector of constant magnitude, then the vector is orthogonal to its derivative. That's an absolute, and that, by the way, is a huge result. Oh my gosh, this result is huge, and because it's really helpful to do things. Whoa, and I'm going to do some examples of this in a moment. If I have a vector of constant magnitude, then the derivatives are orthogonal. And by the way, that would be then the first and the second derivative would be orthogonal, the second and the third. Whoa. How do I know that? Because we started with supposing, and I reminded you that a vector dotted with itself is the same as magnitude squared. So v dot v is c squared. And I'm differentiating a constant. So let's go to a vector value function here. I'm going to do my best here. R of t is cos t, sine t, t. Okay, I'm going to do my best because I'm going to try to draw a three-dimensional motion on the xy plane. This one I can get away with. All right. So, by the way, what are the units of t? Not what might they be, but what do they have to be?
Radians?
They have to be radians. Yeah, they can't be degrees because it wouldn't be a measurement, especially for the t part. You are radians automatically. So I didn't put any restriction on t, so t could go on forever and ever. T could be negative, t could be positive, doesn't matter. T is 0. Then I'm at 1, 0, 0. Remember, that's the x-axis, so I'm here. Now, t is going to increase. Now, on the xy plane, increasing means this way. Remember, increasing is always counterclockwise. Right? Think xy plane. As your angle's increasing, you're moving counterclockwise. So on my xy plane, I'd be going this way as t increases. So if I replace t with pi over 2, well, pi over 2, I have 0, 1, but I would be pi over 2 units high, so I'm going to kind of curve up. Now when I get to pi, I'll be negative 1, 0, pi, and then when I do 3 pi over 2, now when I'm standing on top of the z-axis and I'm looking down, especially if I close one eye, what do I actually see? I see circles. What is this actually? Well, everyone knows. It's a slinky. Another name for that is a helix. Yeah, that's the appropriate term. Any biology folk here? Do you ever use helix? Helix?
A couple times, yeah.
Yeah, for what?
DNA.
Yeah, DNA strands. It's a helix, a slinky. Your car is sitting on top of coils, right? It's the same idea. So when I'm looking up, I see this. This is why I chose this one, because you can all picture this, even though I can't really draw this. This is a very interesting shape. It goes up and up and up and up. One of the things we want to do over the next couple days is describe things like velocity and acceleration and different things, but today we're going to talk about arc length and some other things. But when I'm looking at this, what is the length of this? Well, let's start actually with, let's start with the length of this. What is the length of this shape? Okay. Well, it'd be cos squared plus sine squared plus what? T squared, all under the root. And that would be 1 plus t squared under the root. So, is that a constant? Is that a constant?
No.
No. What if? Okay, this is my helix. T grew as the angle grew. What if I replace t, just say, I don't know, 2. I'm going to replace t with a scalar rather than a variable. This is really useful, again, not to draw, but to be able to picture this in your head. What is happening now? Same idea. You know, as I'm moving around this way, well, let's see, I was 1 unit out, but I was 2 units high, and then I was pi over 2, so I'm just going to get a circle, aren't I? Tell me about my circle. It's a circle 2 units above the xy plane. Oh, so all of my vectors, because I started 2 units high and now I moved in a circle. Is everybody okay with that idea? Now what about my magnitude? Tell me about the magnitude of this one.
Well, it just keeps going the same place, but
That's now a 2 squared, isn't it? So this would be root 5. So does this vector have constant magnitude? Yes, even though it's not a vector of constants. Okay? So tell me about the derivative of r of t.
0, right? Orthogonal.
Well, no, the derivative of r. I'll just do it right here. What's r prime of t? Well, that would be negative sine, sorry, I messed up my thing here, positive cosine 0. Now, if I perform the dot product of those two, I have negative cos times sine plus sine times cos plus 0. Isn't that 0? That's exactly what it's supposed to be. Oh. So I created a vector of constant length, even though it wasn't a vector of constants, just to show you, yeah, that's really not a complicated concept that I could have vectors of constant lengths, particularly when you got sines and cosines. That definitely makes it much easier. Okay? Everybody cool with that? This is a fun one, and we spend time on this one, and I'm going to spend some time on the circle. Now, in the recorded lectures, I do some of this. I do some two-dimensional pictures because they're easier to see when we do velocities and accelerations and all that. And a lot of it, you'll be able to see where it's going. So the big result for today at this point is I want to go over arc length. So I'm going to review what you did in Calc 1, then what you did in Calc 2, so we can do it in Calc 3. You say, well, arc length doesn't seem all that important. Interestingly enough, there is only one topic that is covered in all 3 semesters. Only one. And it is arc length. So arc length must be kind of important. You realize that in all of calculus, there's only one thing that's covered in all 3 semesters, and it's different all 3 times. So in Calc 1, we did arc length from the standpoint that we had a function, y is a function of x. And in Calc 2, we did it by parameterizing it so we could extend and do more problems. And in Calc 3, we now need to do it so we can do it in 3 dimensions. And you're going to find the segue from 2 to 3 is the easy one. It's very easy to extend it. So, some of you were in my Calc 1. I don't expect that you remember the details, but hopefully you remember the results. Okay? Usually we'll say that's, x1, y1, and that's x2, y2. And my curve, we'll say is y as a function of x. Okay? I want to find the length of the curve. And here's the way I always want you to think of this. Okay, I need to get to the door. Well, I have two paths. I can this, well, kind of this over here, and go around Jill there, and okay, I made it to the door. All right, was my path linear? No. Boy, it would have been a heck of a lot easier if it was, because then it would be a simple calculation, but it wasn't linear. I could have gone over the top, but that still wouldn't have been linear, because it would have been three-dimensional. So I want to calculate that. Well, the most crude estimation would just simply be the length of that line segment. Do you agree? That would be a crude estimation. Obviously, it would be too short. So what if we did this? I do a few line segments. And I said, let's find the length of each of those, because we know the length of a line segment. That's distance formula from remedial algebra, right? The square of delta x plus the square of delta y square root. That's actually trivial mathematics. Would that be a better estimation? Can I go better still? How? More cowbell, right? I mean, more line segments. We all know that. Oh, how many line segments? Lots. You smell it? Yep, smells like a lemon. Okay, this is what you did in Calc 1. So I need to do the algebra from the Calc 1 so that we can do the algebra from the Calc 3. I could just give you a formula and it would have no meaning, and nobody in the right mind would ever figure out where it came from. And that's exactly what all the calculus books do. The development of arc length isn't in any calculus book that I've ever seen. I don't think the authors even know, but they know the formula is correct. It's like surface area by rotation. They give you the formula. They have no idea where it came from, but it is the right formula. So let me take one of these. Let me super inflate it, okay? I'm going to take one of these sections here, and let's pretend this is fairly small. We always use S for arc length in mathematics. Don't ask me why. Probably the same reason we use M for slope. My actual guess is maybe it comes from really some obscure Latin or something. Yeah, why do we use M for slope? Yeah. But we always use S for arc length. That's universal in all three semesters. So the actual change in arc length, the actual change in X, the actual change in Y, we call this one the differential change. Now in Calc 1, you maybe remember the problem where you were, right, the tangent line left the curve and you used the tangent line to estimate the curve. So in other words, you were using the dy to estimate the delta y in f of x plus delta x. That goes way back, like literally 5th or 6th lecture of Calc 1. We're going to do something similar in this class. But the notation, so the incremental change on the line segment, dx is equal to delta x, because the change in the x is the same for both of these, isn't it? And the change in the y is the same. We like that. Generally speaking, the independent variables, the incremental change and the actual change are the same. It's always the dependent variable that you're going to estimate. So what we want to do is we want to estimate delta s with ds. It cannot be equal. The equal would come only if I take the limit as delta x approaches 0. That's the only way they're equal. Okay? So this is what we call asymptotic convergence. Very similar to what you did with Taylor series and things like that. All right? So let's do our simple mathematics. Shouldn't this be delta x quantity squared plus delta y quantity squared under the root? Yes? Now, off to the side. If I said a squared plus b squared, could you factor out an a squared for me? How would you factor out a squared?
1 plus b squared over a squared?
Yeah, do you all agree that, oh, okay, that's not that hard. Why am I saying that? Because I want to factor out the square of delta x. So if I factor out the square of delta x, then won't that be, or the way you said it like that, won't that be 1 plus the square of delta y over the square of delta x, all under the root times the square of delta x under the root. So just a delta x on the outside. Delta y can be negative. Delta x cannot, because I'm moving left to right. So there's no absolute value. A lot of times we fudge things, shouldn't there be an absolute value? No, delta x is moving this way. Delta y can be negative, not delta x. Okay, so far so good? Well, how about if I rewrite that as 1 plus delta y over delta x quantity squared? Okay, great. Now, this value is equal to that. So I want to estimate the entire S, which would be the sum from I equal 1 to n of all the little delta s's. Delta S1, delta S2, delta S3. And that would be estimated by the dS's. Cannot be equal. But there's going to be a limit in here somewhere that I can finally throw the equal sign in there. And that, of course, is now this. All right, I said there's n of them. So 1 plus delta y of delta x, and now I'll call it delta I. I'll say the ith one. Right, I just said generically, but technically this might have been the first, might have been the second, it might have been the third. We'll call it the ith one. Okay? S equals the limit as the norm of the partition approaches 0. And I'll remind you guys what that means. You never actually do the calculation, you just express it in these forms. Okay, think Calc 1 for a moment now. Well, this is Calc 1, but I'm even further back. When you first found areas under curves, do you remember what you did? You randomly split it up into rectangles of various sizes. And then you took any place in the interval to square it off. Didn't matter where, left, right, middle. Sort of a random nature. You randomly partitioned this, you chose random places in the interval, and then you said, if I add up all of those areas, I'm actually going to be really close to the actual area. Equal will come by taking the limit. And so what you did was, you said, let me take the limit as delta x goes to 0. But the problem is, if all the delta x's are independent of each other, I can't say as delta x goes to 0, and you can't take a limit of more than one thing. So the norm of the partition literally means the largest partition, the largest magnitude, the largest width. Now those in my Calc 1 class, I'm going to bring back some painful memories. Do you remember the shrink ray? Oh yeah, Zachary. Okay, just so you have a little bit of background. Okay, I've been trying to join the evil league of geniuses. And to do so, you have to have a few things. One is you have to have an evil lair, I do, and you have to have the evil weapon. Mine was the shrink ray. And so what I do was, I find the biggest person in the class, I'm going to shrink it down to 1 point. By the way, later I just pour water on you, you come back, but it's kind of traumatic. And so everybody, so at some point, you're the biggest person in the class, aren't you? And then I shrink you down to 1 point. This is absolutely verbatim what this means mathematically. In other words, if the largest width is approaching 0, now there's a new largest width. So now it's approaching 0, so now there's a new largest width. Eventually, doesn't every single width have to approach 0? If you're always going after the largest width, so I'm always doing the shrink ray on the largest person, eventually even the smallest person will be the largest person. Even the smallest width will eventually be the largest width. So that's the notion, that's what that means, the norm of the partition. And you notice we use vertical bars. That means the largest magnitude. But delta x, the only measurement is its width. So magnitude refers to length. Later in this course, we're going to do this where the magnitudes will be areas or the magnitudes will be volumes as I subdivide things. So we use the same notation. So this just means the largest delta x is going to 0. That's it. Now we know something about limits. We know the limit of a sum is the sum of the limits. That's absolute, and that's something hopefully you proved. When we did epsilon delta on day 2 of Calc 1, we proved that limit. We proved that. It's actually very easy to prove. Why am I mentioning that? Because that means this limit can move in here. The limit of the sum is the sum of the limits. Now, one thing about limits, the limit of the composition of functions is the composition of the limits. So in other words, if I have a function of something and I want the limit of the function, it's the function of the limit. That's an absolute. That means it moves inside the square root. I could keep rewriting the limit, I just don't like to, it takes too long. The limit of a sum is the sum of the limits. The limit of the 1 is just 1. So now I move it in here. But now I have one delta x at a time. So now I'm only taking the limit of one of these guys. Now I want to move it all the way to the inside. So now what I have is there's only one delta x that I'm taking the limit of. So right now, inside that square, I have the limit as delta x approaches 0 of delta y over delta x. Does everyone understand? That's what I have now. I'm inside the parentheses. I only have one delta x. This is exactly what this is going on. So the definition of the derivative, I have it on the outside. I moved it all the way to the inside. We've done this today already. There's another name for this. Isn't this the definition of the derivative? But not the f of x version, no. This is the dy dx version. This is defined to be this. Why is that a good thing? Because when you wrote the Riemann sum, you never calculated the Riemann sum. You used the Riemann sum so you could translate it into the definite integral. If you guys remember, you never actually calculate a Riemann sum. So that means that this limit, after all is said and done, is equal to the integral. In this case, we'll say x1 to x2. Okay? But of what? Because if you remember from Calc 1, you translated directly. The problem is, how do you get from here to here? You get it here. You get it by moving the limit inside, inside, inside. So if you go back to any calc book and look, this is the formula for Arclength. And I guarantee your book has the formula correct. And probably none of what I just did. I do a lot of that. I show you how to do things and you look and go, I can't find this anywhere else. This is the only way it can be done. There is no alternate version. You don't need to do the path, you need the result. Problem was, there's basically only 3 functions you can find arclength of. So the vast majority of the time, the textbooks say, set up the integral to find the arclength. You say, what? Set up the integral. Let's do a simple one. Let's say y is, y is, I don't know, x cubed. Let's start simple. Okay? And I want to find the arc length from, let's say, 0, 0 to 2, comma 8. So I want you to find from here to here. Pretty simple problem. Cubic, right? Really, that's just not that complicated to understand. So my arc length integral is going to be the integral from 0 to 2 of 1 plus, well, what's the derivative of this? 3x squared. What's the square of that? 9x to the 4th. Everybody see where I'm getting that? And good. And so then what did you do in Calc 1? You waved at it as you moved on to the next problem. Why? No math exists to do that problem. That's not possible to do. No. Just because you have an integral doesn't make an integrate. For everything that can be integrated, there's an infinite number of variations that can't. Think of just a sine function. Now replace the x with a function of x and you probably can't integrate it. Almost every function that exists gives you an integral that has no antiderivative. That's the problem with this. That's why it always said set up the integral. This is a final exam question I give. I say set up the integral. It can't be done. Well, can't I use Calc 2 techniques? No. No, and we're okay with that. But that's because we're very limited. So then we move to Calc 2. Now I'm going to accelerate this part. We move to Calc 2 and we have the same, everything's exactly the same. And I have this problem up here. Okay? But in Calc 2, we do something different. Because in Calc 2, we learn how to parameterize curves. All right, I want you to do the same thing I asked you before. I said before, factor out the a squared. Now I'd like you to factor out, how about c squared? Let's factor out the c squared. Oh, but I don't have a c squared. Sure you do. I just wrote it. What would I get?
A squared over c squared plus b squared over c squared.
Okay? I want you to factor out the square of, I don't know, delta t. Algebraically, does that sound? Yes, absolutely. Now I'm going to do the exact same problem with the Riemann sum and the limits, but I'm going to fast forward to the end. We had 1 plus the square of delta y over delta x before. Now what do I have? Now I have delta x over, I have this squared delta t, okay? When I do my Riemann sum and I take the limit as the norm of the partition approaches 0, now it's the delta t, not the delta x's. Delta t, but t is an external parameter that I introduced to make the problem actually easier. I'm going to go dot, dot, dot. I'll write it from t0 to t1. You have to figure out what the t's are. Right? I have x's. You'd have to figure out what is the t when you do this, but that's actually easy. What's going to be my integrand? Well, when I took the limit, didn't delta y over delta x become dy dx? When we did the limit just a moment ago. So what's the limit of delta x over delta t when the delta t is going to 0? Won't that be dx dt? This is what you did in Calc 2, integrate with respect to t. In Calc 2, you did arc length of a parameterized curve because you didn't need to reinvent the wheel. You just took the result from Calc 1 and then you did this instead. And now when I do my Riemann sum and I take my limit and I move my limits inside, right, the delta x over delta t becomes dx dt when I take its limit. So I get this. Oh, cool. Now all of a sudden there's a whole bunch more problems that I could do that I couldn't do before. This allows me to do so many more things. So how is this supposed to help me in Calc 3? All right. I think you know these. I'm moving in 3D, how's that? I'm moving in 3D on my vector value curve. X of t, y of t, z of t. And let's say t is simply going to be between a and b, whatever. How can I find the arc length of this guy? Well, if I do the same thing, take a bunch of little short line segments, and I find the length of the line segment, don't we now know how to do that in 3D? It's the 3D Pythagorean theorem. Oh, so I'd go square, square, square. So I'd have a delta x quantity squared, a delta y quantity squared, plus a delta z quantity squared under the root. And now what am I going to do? I'm going to factor out the delta t. I'm going to do all the Riemann sum and everything exactly like I did before, except that I now have, what? A third term. The algebra to prove this is actually trivial. Why? Because everything I wrote is exactly the same, except this would now have this. As we know, because of the three-dimensional Pythagorean theorem, this is now the length of the line segment in 3D. Do you agree? Does everybody understand? We know this. I don't have to prove this. So I do the entire problem, and I get this. And this is arc length in 3D. I told you it would be easy in 3D. It's just an extension of 2D using our three-dimensional Pythagorean theorem. Now, is it still possible I might not be able to integrate it? Yeah. If I just randomly made up a vector valued function, we probably couldn't integrate it. So I actually wrote one down that will work. Hopefully I wrote it down. Okay. By the way, I have to reverse engineer sometimes because if I just made one up off the top of my head, it's not going to work. All right, let's consider r of t is 3/2 t squared, 6t, 4t to the 3/2, and t is between 0 and 4. You always have to give the range of values for t, because otherwise the curve would go forever, wouldn't it? It's infinite in every direction, so I've got to give you a cutoff here. What I want to do is find the length of this curve. I'm not going to draw it. I can't picture what that looks like in my head. My gosh, it's horrible. But I don't need conic sections. Conic sections were for surfaces, very specifically surfaces and only surfaces. That's the only thing we ever use conics for in this class. I'm just moving through space, right? When t is 0, I'm clearly at the origin, and now I just sort of, in that t equals 4, I'm over here. I want to know what was the path that was traveled, how far did I go? So that's x of t, that's y of t, that's z of t. So dx dt is what? Let's calculate each one of these. dx dt is 3t. dy dt is 6. And dz dt is, that's 3 halves. 6t to the 1 half. Next, there's kind of an order that you want to follow so you don't get lost. So the next thing I want to do is this. So what is this quantity? This is the part that's going under the root. So I could go ahead and put the root if you want, or you can do it after. So this is going to be, help me out here.
9t squared.
9t squared
36
plus 36,
Thirty-six
36t.
36t. So technically, this is what is called the arc length parameter. The thing I'm integrating is always called the arc length parameter. Okay? I got to integrate this. Well, hold on a moment. 9t squared plus 36t plus 36. If I factor out a 9, I'd get t squared plus 4t plus 4. Do I recognize that? What is that, Will?
That's t plus 2 squared.
That's t plus 2 quantity squared, and all of this is living inside a square root. Is that a good thing?
Yeah.
That's a really good thing. It means I will be able to finish this problem. Because I manipulated the problem so that the integrand ended up being the square root of a perfect square. Is that the case normally? No. That's why you generally can't integrate the arc length problems, because what you have under the square root is rarely a perfect square. Okay? So, would it be safe to say that this is just the square root of this? Which is what? 3 times t plus 2. Whoa. So my arc length is the integral from 0 to 4 of 3 times t plus 2 dt. Now, because that's a simple polynomial, you might find it easier to just go ahead and multiply the 3 back in. It doesn't matter. But it might be easier if I just go, okay, 3t plus 6. Now, this is the only part of the course for a very long time, in terms of the course, not in terms of days. This is the only part where we actually do any integration, because the only way I can find arc length is to, at some point, integrate that. So I have the integral from 0 to 4 of 3t plus 6 dt. So what's that going to be? 3 halves t squared plus 6t from 0 to 4. What's that? 24 plus 24, or 48. So we were able to pull that one off. So I have this 3-dimensional motion. I picked from point A to point B. You found the length that was traveled, if you will. If there were units, what kind of units do I have there? It's arc length. So I would have length units. What are the kinds of units that we are subject to in a class like this? Well, we've already talked about force. We've talked about work. Okay, later we might have areas, volumes. So in this case, it would be a length unit. So whatever length units you'd be using. Not critical at the moment. Near the end of the course, units become a bigger deal because of the types of problems that we're going to be finding. And sometimes we're going to be finding things that have rates, might be volume per second, just different things. And so being aware, okay, just aware is good enough. That's the answer. I don't need you to put units on it, but understanding I found a length of a curve. So it would be length units if I give you units involved. Okay?
Would this be a magnitude? the vector?
No, this isn't the magnitude of anything. This is how far did I travel. So if I did it in two
That's not
dimensions,
magnitude?
I wrote the length of a curve, so how far did I travel? Just how far did I travel? It's not a vector though. See, I'm moving along a curve. That's why you wouldn't use magnitude in this case.
Okay, right.
Yeah. If I think of a vector, I can talk about the magnitude of a vector. That's true. So in a sense, you'd be saying, it's kind of like saying, if I asked you for the magnitude of this vector, you would say this squared plus this squared plus this squared, which would give me completely different things, wouldn't it? They wouldn't look the same. And then I'd say, all right, that's the magnitude of that vector for all values of t. But I'm not asking you for the magnitude of any particular value of t. I'm just saying how far did I travel. So another way of thinking about it, I'm going to give you a glimpse.
Distance versus displacement?
Well, not exactly. Next day, we're going to define velocity and acceleration. If r is position, think of position as being how far am I from the origin. So in other words, if r had units, they'd be length units. But I'm differentiating with respect to time, which means the derivative of r would now be length per time. So what do you suppose the derivative of r is? Velocity. Speed is actually, believe it or not, the magnitude of velocity. And then what do you suppose the derivative of velocity would be? Acceleration. That's next day's lecture. That's why that's so important. Now magnitudes come into totally different. So what we're really doing here is we're saying, think about, I'm moving, I get in my car, I drive a particular speed for a particular period of time. Now you can tell me how far you travel. But that you had to actually physically drive. You see what I mean? You can't just look at the original vector. So this I drove along this curve for a little while. How long did I drive? Oh, about 4 seconds. Does that help you from that standpoint?
Yeah.
So it's a slightly different. We are doing magnitudes, but this would not be a magnitude in this case. But I am looking at, is this a magnitude of something? Yes, it is.
Yeah.
It's the magnitude of the derivative.
Yeah.
Oh, it's the sum of the squares of all these. This is the magnitude of the derivative, exactly. So that's important. But it's not the magnitude of the r. That's the thing.
What is conceptually, what does the derivative of a vector mean?
Well, in this case here, because our independent variable we're calling time, then r is motion through space. So if I'm moving on through space, there's always got to be something that I'm relating it to. I'm this far from home, if you will. Okay? So the derivative of r, it would be how far I am per second. So how fast am I moving away from home? And then the derivative of that would be how fast am I accelerating away from home? That's going to be basically the next day's lecture. That's most of the stuff. It gets kind of cool the next couple of days because we can start describing motion and coming up with conclusions and applying it to real life situations. And you can say, oh, okay, that's why, that makes sense. Okay? And so, particular types of motion are much easier to describe when I can do it this way. All right, would you go ahead and stop for me? Let me do the roll thing.